Hello, my name is Raina D. Jute, and welcome to my Module 14 problem-solving video. In this video, we'll go over 5 LeetCode problems, and I want to focus on not just the solution, but the reasoning behind it and how I got to the solution. A lot of these problems were harder than I expected, so I couldn't just figure them out on my own. I had to study, look things up, and ask AI to explain things until they made sense. So one thing I noticed while working on these problems is that some of these patterns in the LeetCode problems actually showed up in my project this week in a different form. I'll point those out as I go because I think it helped me understand both things better when I saw them connected. So let's start with the first problem, which is validate binary search tree. This problem is a Java problem, which I want to acknowledge up front because Java is still not super intuitive to me, especially in this module where the backend was written in Java, but I didn't create the backend. I just used React Native to sync to it. So I leaned on AI a lot to help me understand both the algorithm and the syntax. So the problem gives you a binary tree and asks, is this a valid BST? The rule is that everything to the left of the node has to be smaller than it, and everything to the right has to be bigger. So my first instinct, because I've seen similar problems to these in the past, was just to check each node against its immediate children. So left child, smaller, right child, bigger, done. But that's wrong. And when AI explained it to me, it made a lot of sense. So the rule isn't just local, it's about the entire subtree. If your root is 5 and its right child is 6, that looks fine, but if that right child has a left child with the value 3, locally 3 is less than 6. So it seems okay, but 3 is sitting on the right side of a tree whose root is 5. That violates the BST rule. The naive check misses it. So the real insight is as you go deeper into the tree, you carry the valid range with you. Every node has a minimum and a max it has to fall inside, and those boundaries get tighter with every level that you go deeper. So this helper validate right here takes the node and a valid range, a minimum and a maximum. If the node is null, we hit the end of the branch and then we return true. If the value is outside of the range, then we return false. Then we recurse. Going left, the max tightens to the current value. Going right, the min tightens. So we start the whole thing with this long min value, long max value. Anything goes at the root. I used long instead of integer because node values can be as extreme as integer min value, and AI caught that edge case when my first solution was failing. I was actually doing something structurally similar in my Expo router auth gate. The root layout sets up providers and wraps everything. The child layouts, the app group layout, the courier group layout, each inherit a constraint from their parent and enforces it for everything below them. So a customer-only user can't reach courier routes the same way a node that's too large for its subtree fails at the BST check. The constraint is defined at a higher level and carried downward. I didn't realize those two things were the same pattern until I started working through this problem. Moving on to problem 2, which is exchange seats. This is a MySQL problem. So this problem gives you a seat table with an ID and a student name. You need to swap every pair of adjacent seats. So seat 1 swaps with seat 2, seat 3 swaps with seat 4, and so on and so forth. If there's an odd number of student, then the last one just stays. What surprised me is that you don't need to actually move any rows around. So SQL has a case statement that works like an if-else statement in JavaScript, and you can use it to just display a different ID for each row depending on whether it's odd or even. So for an odd seat, we show ID +1, that student moves forward. Even seats, we show ID -1, that student moves back. Last seat, if it's odd, we leave it alone. This is basically the same structure as my role-based routing logic. So in app-index.js, after login, I check, does this user have a customer ID, a courier ID, or both? And based on that combination, I route them somewhere different. It's a case statement, but in logic form. So we evaluate a condition about the current item, branch to a different behavior. And just like in exchange seats, the edge case has to be handled explicitly. So in the SQL problem, it's the last odd seat. In my project, it's the user with neither ID, which shouldn't happen but has to be accounted for anyway. So ID %2 is modulo. It gives you the remainder when dividing by 2, so it tells you if the ID is odd or even. The subquery just gets the total row count to check for the last seat. And then the case evaluates top to bottom and stops at the first match. So the specific edge case has to come before the general rule. I forgot that ordering on my first try and I kept getting wrong answers. And once AI explained that case is short circuit evaluated, first match wins, it made sense why the order matters here. So problem number 3 is tree node. This is also another SQL problem. So you have a table where every row has an ID and a p_id, which is the parent's ID. So if the parent ID is null, there is no parent. The task is to label each node as root, inner, or leaf. So root is when the parent ID is null, leaf, this node's ID never appears as anyone's parent, and inner is it has a parent and is also someone's parent. So the key question is, how do I know if a node has children? And the answer is just, does its ID appear anywhere in the PID column? That's a set membership check. Does this value exist in that set of values? So the subquery builds a list of every ID that appears as parent. If the current node is in that list, then it's an inner node. That's where PID is not null inside of the subquery is important. Including nulls in an in comparison causes weird behavior in SQL. AI flagged that as one of those things that doesn't have a clean, intuitive explanation. You just kind of have to know it. And this, does this ID appear in that column, is the same way that I thought about the courier delivery list. An order belongs in the courier screen if its courier ID matches this courier, or if it appears in the pending list with no courier assigned. I was asking, does this order belong to this courier, the same way the SQL is asking, does this node appear as someone's parent? Both are translating a relational question into, does this value exist in this set? And then problem number 4 is department top 3 salaries. I had absolutely no idea how to solve this problem, so this answer is 100% AI generated, but I'm going to talk through what I learned as I was trying to find the answer. So the problem asks you to find employees with a top 3 salary in their department. The keyword is unique, so if 4 people tie at the second highest salary, all 4 of them count. That rules out a simple limit 3 because you need ranking logic that handles ties, and that's where this dense rank comes in right here. It's a window function. So a window function does a calculation across related rows without collapsing them the way a group by does. Dense rank assigns ranks where ties get the same number and the next rank doesn't skip. So 2 people tied at rank 2 means the next distinct salary is rank 3, not 4. Regular rank would give rank 4, and we would miss valid employees. In this problem, I also learned what a CT is. So a CT stands for Common Table Expression, which in SQL is a temporary named results set that you can reference within a single select, insert, update, or delete statement. And it's defined with the with clause, which is the first word we see in the solution. CTEs function like temporary views or virtual tables that exist purely for the duration of the single query's execution. So in this problem, the CTE computes a rank for each employee within their department. The partition by makes the ranking reset per department. Then the order by salary descending puts the highest salary at rank 1. The outer query filters to rank 3 or below. The CTE exists because you can't filter on a window function alias in the same where clause. SQL processes where before the window results are available. This problem is about ties, multiple things that are equal deserving the same treatment. That maps directly to a bug I fixed this module in my auth context sign-in. It was normalizing customer ID but not courier ID. The login response has both courier_ID in snake case and courier ID from a spread, but they're the same value. So when I compared user courier ID in the routing logic, I was getting undefined because I was reading the wrong representation of the same thing. It's the same risk as using rank instead of dense rank when multiple representations of the same value exist. If you don't handle them consistently, then you get silent wrong then you silently get the wrong answer. The fix in both cases is be explicit about which representation you're using and be consistent. And this last problem is the problem that confused me the most. So a stadium table with an ID, a date, and a visitor count. We find all records that are part of a run of 3 or more consecutive IDs where each had at least 100 visitors. My first attempt was checking each row's neighbors, but that only catches rows in the middle of a qualifying sequence. It misses the first and the last rows of each group. I got stuck about 100 times in this problem and asked AI to explain the solution concept. And it introduced me to something called islands and gaps pattern. And I want to try to explain it because once it clicked for me, it started to make a little bit of sense. So if you have consecutive IDs like 5, 6, 7, 8, and you number them with row underscore number, you get 1, 2, 3, 4. Then we subtract. 5 minus 1 is 4, 6 minus 2 is 4, 7 minus 3 is 4, 8 minus 4 is 4. They all give the same number. Now if there's a gap, IDs 5, 6, and then 9 and 10, the row numbers after the gap fall out of sync. So 9 minus 3 is 6, 10 minus 4 is 6. It's a different constant. The gap created a different group ID automatically, so I can group rows by that constant and count how many share it. Groups of 3 or more are qualifying runs. I literally wrote this out on paper with the example data before I tried recording the video because it was just that complicated for me to understand. So the first CTE, filter to busy days and compute the group ID. The second CTE is find groups with at least 3 members. Then the outer query gets the actual rows back. This problem is fundamentally about merging disconnected pieces of data and figuring out what belongs together. My courier delivery screen does the same thing. I have 2 separate API calls, one for pending orders with no courier assigned, and one for orders that have already been assigned to the courier. I merge them client-side and deduplicate by order ID. An order that's been claimed by my courier appears in both of the responses, so I have to keep only one copy. The stadium problem identifies what belongs to the same island by computing a shared group ID. My courier screen identifies what belongs to the same courier's view by merging an on order ID and deduplicating. Both of them are asking the same question. I have data from multiple sources. How do I figure out what belongs together and avoid counting the same thing twice? So those are all 5 of my LeetCode problems. What I actually found interesting looking back is how many of these patterns showed up in my project this week without me realizing it at the time. Carrying constraints downward through layers, that's in the BST problem and in my auth gate. Branching on conditions with explicit edge cases, that's in the exchange seats problem and in my role routing. Set membership as a way of answering relational questions, that's in tree node and in how I thought about the courier order list. Consistent representation of equal values, that's in dense rank and in the courier ID normalization bug. Merging data from multiple sources and deduplicating, that's in islands and gaps, and in the to-call courier fetch. I don't think I would have noticed these connections if I hadn't had to explain both things out loud. That part was actually super useful. But that's all I have for this week's video. Thank you for watching, and I will see you on the next one.